Hello. In continuation of the discussion that we had on the last video on the convergence of Fourier series to the function f when f is a periodic differentiable function that is piecewise. So, basically that means function when the function f is a piecewise differentiable periodic function, that means its derivative function, that is f dash of x, is a piecewise periodic function. So, with period L, if such a function f, what is its Fourier series and its convergence? It converges to the function f itself whenever x belongs to the period interval minus L by 2 to L by 2. So, as of now we will just we are only talking about the open interval minus L by 2 to L by 2, and eventually we discuss at the end. Once we prove this, we will discuss the endpoints also, or the points of discontinuity. So, these things we will see. So, anyway, so there is no point of discontinuity because we are considering differentiable function, that means it is continuous function. Okay. So, so discussing about the proof of this, we started with this. We consider the series partial sums of that series, and we just simplified, and in between we define what is dn. And then so when you substitute and you observe that dn is this, dn of this function is actually this simple sine function involving simple sine functions, and also we observe that it is an even function, and then it becomes this partial sum becomes this once you change of integration, change of variable in this integrand, t minus x equal to x dash will give you so this type of function. So, this partial sum, we only so far we consider only partial sum of that series, Fourier series, and we end up having this expression. So, what we do now, we will just rewrite this. So, we will rewrite and see that as n goes to infinity, this converges to fx. So, that is what we are going to show. So, we will show as n goes to infinity, this partial sum of the series, Fourier series, it converges to fx. Let us see how we will do this. So, I am just going to do some manipulation here. So, we will write 1 by L. So, it is from 0 to L by 2. What I do is I just subtract something from this quantity so that I have to add. Once you subtract, and you also have to add. So, we are fixing x we are fixing, and t is the integrating variable. So, we write f of x plus t minus f of x plus x plus and x minus we have defined, that means limit of f of t as t goes to x plus as t goes to x minus, that means coming from right side or left side of x, that limit is this f at x plus and x minus. Okay. And this is what I subtracted, plus from this also you can do the same. So, x minus t minus f of x minus, okay. And then this divide by, and you have this sine n plus 2 n plus half w naught t dt divided by sine w naught by 2 t dt. That is what it is. So, see as t, so t is between 0 to L by 2. So, as t goes to 0 and I have the quantity, and this is 0, and you have the top quantity, that is the numerator of this part is 0. So, as t goes to 0, fx minus fx plus plus fx minus. So, what happens as t goes to 0? If you look at it as t goes to 0, this quantity becomes f of x, basically 2 times f of x minus f of x plus f of x minus. Because this is continuous function, is anyways actually is 0. If x is in between, if x belongs to minus L by 2 to L by 2, if it is in the open interval. If it is the endpoints, we do not know really. So, if it is like this, your function is like this, if it is repeated from minus L by 2 to L by 2. So, you see this endpoint here is the different values. Okay. So, 2 times of this is really not you do not know exactly what this means. Okay. So, if x is this, if x equal to, if you take minus L by 2, this difference average value is here. So, you cannot say that. So, in that case we do not know. So, it is not 0. Okay. So, you actually show that it is actually 0, it has to be 0, otherwise this integral does not make sense, because denominator we have 0. So, numerator has to be 0. So, anyway, so that observation. So, just to avoid that, and we also know that we also, I will just remove this here, we also know that these limits, limit f of x plus t minus f of x plus divided by x plus t minus x plus, that is t. So, this limit t goes to 0 is nothing but, this is anyway x side, x positive side minus that limit at limiting value. So, this something like this here. So, you take some value here, f, this is x plus t, this is x plus. So, that you come from the value of the function from this this limit. So, that this is actually f derivative at x plus at this value. So, this is the derivative at x plus. If it is piecewise, this may be different from the other side x minus. Okay, it is not need not be same, because what we considered is a piecewise differentiable function. Okay. So, this need not be same as this. So, this is what it is. So, it exists. So, because we assume that it is piecewise differentiable function, so this is finite. Similarly, we have t goes to 0, f of x minus t minus f of x minus divided by t again, x minus t minus x. Okay. So, this is also f dash at x minus. This is also finite, because that is what we assumed. So, to get this quantity, we only divide, we need to divide with t. So, if you divide t, you have to multiply t. So, you rewrite, this is the most elementary way of doing showing the convergence of this Fourier series. So, I write this f of x plus t minus f of x plus f of x minus t minus f of x minus, this I divide with t for both the parts, and also I write t divided by sine omega naught by 2 t. Okay, into that whatever remaining part n plus half omega naught t dt. So, I just multiplied, anyway so t is from 0 to L by 2. So, t is non-zero, so you can always divide. As t goes to 0, does it mean, it does not mean that t is 0. So, t goes to 0 means t is non-zero and it is approaching 0. So, I can always divide L, divide with t both sides. So, this quantity I call something, the quantity here I call it something else. So, once I add and subtract, I have to, so here I subtracted, so I have to add. So, that quantity is whatever is left with is minus L 0 to L by 2. I subtracted, so I have to add f of x plus f of x minus into this quantity sin n plus half omega naught t by sin omega naught by 2 t dt. This integral is addition, so I have to add here also 1 by L 0 to L by 2. This quantity says anyway nothing to do with that integrand variable. So, I write this outside f of x plus f of x minus times integral 0 to L by 2 sin n plus half omega naught t divided by sin omega naught t by 2 dt. So, this quantity, this integral, you can actually show that is actually 1. Okay. So, we look at this integral plus this integral. So, before before I allow n goes to infinity, this is actually your Sn. I first show that eventually I allow n goes to infinity. So, before to do that, before doing that, we will just take these two integrals, we will handle these two integrals separately. So, we will start with the first this one. So, one observe that this integral 0 to L by 2 sin n plus half omega naught t dt divided by sin omega naught t by 2. This value, if you directly evaluate in terms of sines, it may be little tough. So, instead you write as sum. So, this is simply, so you just because this is a even function, because this is a sine function, this is a sine function, so it is an even function. So, this is actually because the integrand is an even function, you can write from minus L by 2 to L by 2, and this is going to be a sine same function, okay, omega naught t dt by sine omega naught t by 2, and this is equal to half I integrate from L by 2 to L by 2. So, this quantity integrand we will just this is actually dn of x, which I use a primitive expression, that is a finite sum. So, that is partial sums minus n to n e power minus I k omega naught x, okay, omega naught t dt. Now, you can see that. So, once you have this exponential function which is running from minus L by 2 to L by 2 to L by 2, whenever k is non-zero, whenever k is non-zero, this integral value is actually equal to 0. Okay. So, when this is non-zero, only when k equal to 0, which you have minus n minus 1 and so on, you keep on doing up to 0. 0 is the only contribution. When k equal to 0, that is the only contribution is left, and when k equal to 0, this is simply 1, and other values. So, it's a kind, you should write like this. You can take this sum outside, integral minus L by 2 to L by 2 e power minus I k omega naught t dt. So, now you look at the each of this when k is minus n to n. So, whenever this exponential function, when k is non-zero, this is going to be 0, this integral is 0. So, for that reason only contribution will be when k equal to 0. So, when k equal to 0, so that is nothing but minus L by 2 to L by 2, k equal to 0, that is 1 dt. So, this is nothing but L by 2, this is what it is. So, you have this will be L by 2. So, you have finally this whole thing is half of the average value of that is actually half of f of x plus f of x minus, the average value. So, and we also define what is q. Let me define what is q n of x. It depends on n. So, if you write this, let us say not q n, so it is just q. Q of x, if I write it as that first integral integrand, whatever in this brackets, f of x plus t minus f of x plus f of x minus t minus f of x minus by t into t by sine omega naught t by 2. That is what if you define like this, then what happens to this integral. So, you can see that it is well defined function. So, q of t, let us rather. So, let us write q of t. So, x is fixed, when we fix x, it is a function of t, it is well defined for every. So, as t goes to 0, this quantity is 1 sin x by x type, and this quantity is anyways these derivatives are exist as t goes to infinity. No other t value as t between 0 to pi L by 2 there is no issue. So, it is well defined function. So, qt is defined for every t is in 0 to L by 2. Okay. If you do that, what happens to your Sn? Sn is qn, this is q of t, that sine function. So, let us write what happens to your Sn. Sn of x is, what you have is 1 by L 0 to L by 2 q of t into sine n plus half omega naught t dt plus the other integral by the earlier calculation. So, this becomes half of f of x plus f of x minus. Okay. This is what it is. Now, what happens to this? Now, we look at this integral as n goes to infinity. So, we will take this limit n goes to infinity. So, you have this limit n goes to infinity, and this is anyway constant, so that does not change with the limit. So, we only have to worry about this n goes to infinity, what happens to this 1 by L 0 to L by 2 qt sine function sin n plus half omega naught t dt. Okay. So, this is equal to, so I will write, so again, so q of t if you observe this tt goes, this is, what is this one, this becomes, what happens, this is odd function. If you see, replace t by minus t, numerator is same, here this cancels, so you have minus because of sine function, sine of minus t, so minus comes out. So, this is an odd function. So, q of t is an odd function, sin t is an odd function. So, together this is an even function. Okay. So, this integrand is an even function. So, again like earlier we can write the limit of 1 by L, or rather, so 2 by L times minus L by 2 to L by 2 qt sin n plus half omega naught t dt. So, because it is odd even function, so integrand is even, so you can write 2 times that integral. So, you can replace, you can extend it to negative side. So, this is equal to limit n goes to infinity. So, you can write now 1 by so rather half of it, right. So, this is 1 by 2 times. So, you have 1 by 4 times 2 by L minus L by 2 to L by 2, 2 to cancel is the same, okay, and you have qt. Now, we can expand this sine function. So, that is sin n omega naught t and cos of cos omega naught t by 2 times sin n plus half omega naught t plus, and now qt sin omega naught t by 2. For this function you have cos n plus half omega naught t for this dt. So, this is what you have. So, this implies, so what happens? So, as limit n goes to infinity. So, what is this one? This is limit n goes to infinity 1 by 4. So, this is exactly Fourier coefficient of this function with sine and cosine. Okay. Sorry, so I think it should be, this is n, sin n omega naught, this is cos, I expanded, right. So, you have cos n omega naught t. So, this is the Fourier coefficient of sine coefficient of Fourier coefficient, that is the coefficient of sin n omega naught t for this function qt cos omega naught t by 2. So, and we have seen by Riemann-Lebesgue lemma, if q of t is well defined function. So, you start with where you have f is piecewise periodic function. So, f is differentiable function and f is, that means f is a continuous function, piecewise continuous. So, it is integrable function. Okay. And what you have seen is earlier, if f is a square integrable function over minus L by 2 to L by 2, then it is then its Fourier coefficient is, whose Fourier coefficient is actually is going to 0. Okay. So, I will just show you what it is, what I am going to use. So, if you just go back, so you look at this, if you look at this Bessel inequality, so you look at the Bessel inequality and you see this one. So, if f is a periodic function, periodic function which is piecewise differentiable, that means the derivative is derivative exists, that means this integral is finite. So, integral mod fx dx which is finite, and once this is mod x is finite, it is also square, it is also square integrable, square f into f is also piecewise continuous function. If f is piecewise continuous function, f square is also piecewise continuous function, that implies that is also integrable function. Okay. So, that way you what you have is this quantity right hand side, this integral is finite. Once this integral is finite, this number series sigma ck square, that means that is finite. So, Once you have this, by this corollary, which is the Riemann-Lebesgue lemma, the nth term has to go to 0. Okay. So, in that sense, if you use this one here for this function, if f is such a thing, f square is also integrable function. So, if f is integrable, qn is also integrable, you can see this one. So, this will not really see, you can see that this quantity, this first term involving this and second term is involving this, these are a derivative kind of things, they are derivatives, these are f dash of x minus x plus and f dash of x minus, that is the difference by t into t divided by sin omega naught t by 2. See, after when you take the limit t goes to 0, this is what it is. So, these are the derivatives, these are the things. So, this is a fixed quantity and you have a t divided by this as t goes to 0. So, that is where only we have a problem. Only when t equal to 0, this quantity is going to 1. So, it is a constant. So, and you have qt that is well defined for all 0 to L by 2. Even at 0, I do not have problem, it is not bounded. Okay. What it shows is that the limit q of t, only you have worry about t goes to 0. This is a finite number, because you look at this limit, as the limit this goes to, as t goes to 0, this is actually the first term, these two terms will become this and the other term is eventually becomes the itself, it is 1. So, it is not 1, 2 by omega naught. Okay. So, f of dash f x plus minus f dash of x minus divided by 2 by omega naught. Okay. So, 2 omega naught is 2 pi by L. So, you have finally 2 goes L by pi. Okay. So, this is going to be L by pi. So, it is well defined. So, as t goes to 0, this function qt at t equal to 0, it is a finite quantity and it is defined for all values. So, it is a piecewise, so it is a piecewise continuous function, implies qt is integrable function, that means this integral q of t is finite, minus L by 2 to L by 2. Okay. That is 1. Basically, that you compose it with you multiply with cosine or sine, that is actually is a piecewise continuous function is finite, and once this is piecewise, q is piecewise continuous function, its multiplication square is also like that. So, this is nothing but this one. So, it is once this is finite by the Bessel's inequality and its subsequent corollary, that is Riemann-Lebesgue lemma, you can see that the Fourier coefficient, that Cn, Ck there is for Fk, here this whole quantity, this is your Ck for this function qt into cos omega naught t by 2. So, this goes to 0. So, this into this goes to 0, this goes to 0 plus again 1 by 4 times, now 2 by L into this quantity. For this function, this is your Fourier coefficient, this is minus L by 2 to L by 2. So, this is dt plus 2 by L. So, this is this, if you make a 2 brackets. So, this integral is again a Fourier coefficient, say Bn, this is An and this is Bn. So, all once Cn goes to 0, A and Bn also goes to 0, because Ans are simply nothing but Cn and C minus n divided by 2 and 2y. Okay. So, because of that, each of these quantity goes to 0. So, after by taking the limit, so that is actually becoming this limit Sn of x as n goes to infinity, that is nothing but this Fourier series. What happens, that is what is your Fourier series, that is going to be minus infinity to infinity into fx, that is Cn. So, you have Cn e power I n omega naught x, which is actually this converges, that is what happens, right. This limit is a partial sum when I take n goes to infinity, this is what it is, and we have seen that this goes to limit Sn is what we have seen is this, if this quantity is going to 0 and finally this becomes is only this quantity, it is left is as n goes to infinity, this integral is going to be 0, this integral is 0, what we have shown just now. So, what is left is only this one. So, this is actually equal to half of f of x plus f of x minus. Okay. So, this is what you have shown. So, now I can remove this one, that is exactly what you want to show. So, where is this one? If x belongs to minus L by 2 to L by 2. If you choose only interior point of that open interval minus L by 2 to L by 2. Okay. And now since f is continuous function, because you have chosen piecewise continuous function, piecewise a differentiable function. So, that means whose derivative exists at all points, interior points. So, f of x is same as f of x plus is same as f of x minus. So, that means 2 times f at x value, f of x is defined. So, this is exactly your 2x, 2 times f x, half of it. So, you get f of x. Okay. So, it converges, this converges to f x whenever x is in here. Now, the question is what happens at the end points? If, so you remember that you fixed x value. So, x you fixed and they worked with this. If x equal to minus L by 2, let us say, what happens? You look at again this expression, the limit Sx, Sn, if now x equal to minus L by 2. Okay. If x equal to minus L by 2, x is minus L by 2 plus t. So, where are you? So, let's easy to work out. Similarly, you can work out for L by 2. Let's choose x equal to L by 2. L by 2 you have Sn is this one. So, because I wrote Sn in terms of 0 to L by 2, I have chosen x equal to L by 2. If you wanted x equal to minus L by 2, you rewrite. So, when you split this into 2 parts, 0 to L by 2, 0 to L by 2, what you make is you make this 0 to L by 2 as from minus L by 2 to 0. So, that eventually you end up getting this Sn as integral minus L by 2 to 0, and then you can fix x equal to the same expression, you will get similar expression, but x equal to minus L by 2 you can work similarly. Here for this type of expression, for x equal to, argument is easier if for x equal to, if you choose x equal to L by 2. If you choose x equal to L by 2, f of x plus f of L by 2 plus t, that is you are going out of this integral. Once you go out of this integral, because it is a periodic, you are going to, so where is this function value? Once this function, so let me write this one, this function f of x plus t, L by 2 is the end point, L by 2 plus t, because it is a periodic function, repetitive, this is actually repetitive. So, that means it goes back to, so you have minus L by 2 to L by 2. So, whatever the value, so here is actually same as a value here, because it is repeating, it is repetitive. If it is like this, again it is like this. So, what is this value? This value is here, which is same as this here. Okay. So, this is actually kind of, you will see that f of L by 2 plus 2 is nothing but f of minus L by 2 plus t, minus L by 2 plus t, that is what you have. Okay. So, you have this is the minus L by 2 to L by 2, L by 2 plus t is nothing but minus L by 2 plus t, that is what you have here. Okay. So, this is same as this. So, this one minus f of, now L by 2, so L by 2 you have chosen, so you have this L by 2 value, let us say if it is like this L by 2 value, that you keep it as it is, L by 2 plus, right, where is that, yeah, here. So, this is the one. So, if L by 2 plus 1, f of x plus x is L by 2 plus. So, L by 2 plus 1 means it is coming from, so it is again the same arguments, if it is from minus L by 2 to L by 2. So, you want this integral. So, this limit of the function, that is same as the limit of this function, because wherever the values, if you want to look at it, they are nothing but here. So, as you approach here, you are approaching right side, means you are approaching here, because it is repetitive. So, this is same as f of minus L by 2. Okay. And then what happens to the other one? That is going to be f of L by 2 minus t, that is same anyway inside, minus f of L by 2, that is also inside that limit from this side. So, which is well defined, divided by t. So, what is this one? So, this one when you write like this eventually, so f of x plus is nothing but f of L by minus L by 2. So, other part is what you have is which is if you do this one. So, when you add and subtract it, you have to add with f of minus L by 2 plus f of plus L by 2. So, this anyway again the same argument, this divided by t into t divided by sin omega naught t by 2, that whole as a q of t, and then you have here this part will be 1 by L times. So, this is going to be half of this. So, you will have that one qt plus half of t, where q now wherever x is you replace with minus L by 2, and the second part you have plus L by 2. So, with this argument if you do the same thing, Sn of t, Sn of x, that is also going to 0. Sn of x is going to 0, first integral is going to be 0, second integral is now converged to this function, this value. So, when x equal to L by 2, what you have is a limit Sn as n goes to infinity is nothing but when x is L by 2 is actually equal to f of minus L by 2 plus f of plus L by 2 by 2, half of the value. Okay. If x equal to minus L by 2 you want to look at it, you write this Sn not from 0 to L by 2, you take it from minus, you replace over t by minus t and you rewrite from minus L by 2 to 0. Then you view it similar way, you can see that Sn x as n goes to infinity in both cases will be same as this, that you can take it as an exercise. Okay. It is the same way. So, argument is same, fix x and you look at its periodic thing. So, if this is your periodic thing, if you want to look at the values here, they are here because it is repetitive. If you want to look at this side, they are repeating here. So, if you want to here, they are repeating here. So, that is where is the, if you want to look at here, so it is somewhere here, exactly half. Okay. So, just add, if you want, wherever you want to look at some L plus some A plus L, you add up to L, that is A plus L, that is the value of here. Okay. So, that is how if you look at it, you see that this is going to be this. So, the Fourier series that converges to Cn e power I n omega naught x, this is actually converges to, if f is a piecewise differentiable function, f of x, if x belongs to minus L by 2 to L by 2 open interval, and if it is if it is endpoints, if it is this is going to be addition of average value of the endpoints, half of this if x is equal to plus or minus L by 2. So, when this is f x, if your if it is minus L by 2 to L by 2, if your function is like this, if the value here both are same, then it is function at the endpoints. Okay. So, if so this is what you have. So, if f is same, if f of minus L by 2 is same as f of L by 2, then average value becomes when at x equal to plus or minus L by 2, this Fourier series Cn e power I n omega naught x, n is from minus infinity to infinity, is f x for every x belongs to minus, including the points. Okay. Because if you include, so if such that is the case, if this is the case, then we have this is the more general one, otherwise you have only this one. So, only interior point you can always say converges to the function f x, because f is continuous. Here you are not sure, if it is if your function is like this, the value here is both are different. So, it converges at this point, it converges to the average value, and here also it converges to the average value, that is what it means. Okay. So, you will see we have used Bessel's inequality and Riemann-Lebesgue lemma, the corollary of it, and we have shown this convergence of the Fourier series to the function f itself when it is piecewise differentiable function, periodic piecewise differentiable function. We will see the corollary, that is such a if your Fourier coefficients are same, then you have a unique Fourier series. Okay. If you can always define if it is a piecewise periodic function, piecewise continuous periodic function, if you choose, you can construct your Fourier coefficients, implies you have a Fourier series. So far we have not seen, if it is a piecewise continuous function, we have not seen the convergence of this Fourier series to the function f. But if it is a piecewise differentiable continuous differentiable function, piecewise differentiable periodic function, then you have just now seen that the Fourier series, Fourier coefficients again you can easily define, and using the Fourier coefficients you can make a Fourier series that actually converges pointwise. That means you fix x in the Fourier series that converges to, as a number series, it converges to fx. If it is continuous function, because it is anyway continuous function within the open interval, it converges to fx. At the end points, it converges to the average value of the end points. End points, function value at the end points, that is this. Okay. We will see its Fourier series is unique if your Fourier coefficients are uniqueness theorem. So, we can write the uniqueness of the Fourier series. So, if I choose two functions fx and gx, if be two piecewise differentiable function, differentiable periodic functions, and with you have two such piecewise periodic differential functions, then you can define Fourier coefficients for each of them. Let us call this fn, and so it is earlier we have defined cn. Cn is fx into some integral, right, integral with exponential function, that is your cn. So, I am calling it, for corresponding to f, I am calling it fn. So, fn with fn being Fourier coefficients, with Fourier coefficients, let us write with Fourier complex Fourier coefficients, fn is same as gn of gn. This is true for every n. Okay. So, let this is the case. Okay. Fourier coefficients fn such that fn equal to gn for every n. This is what it have. Then what happens? Then f of x equal to g of x. That means f of x is nothing but, we have seen just now seen from this theorem that fx is a Fourier series of f and gx is a Fourier series of g, and we are seeing that Fourier series are also same if the Fourier coefficients are same. That is what is the meaning of this. So, a proof is easy. If fn equal to gn for every n, then cn, which is fn minus gn, which is equal to 0. So, some coefficients are given which is 0, and we know that cn. So, what is the cn? Cn is a Fourier coefficient of f minus g. Okay. If fn is a Fourier coefficient of f, so fn is 1 by L. What is the Fourier coefficient? 1 by L, the complex Fourier coefficient, which is 1 by L minus L by 2 to L by 2 fx e power minus I n omega naught x dx. Similarly, gn, f comma g is nothing but g comma f. So, replace g f with this, these are the Fourier coefficients gn fn. So, wherever you have g, you put g instead of f. Okay. So, f g, so f gn like that. If you do, these are the coefficients. So, what happens to Fn minus Gn? This is a Fourier coefficient of minus L by 2 for f minus g of x e power minus in omega naught x dx. So, the Fourier coefficient of f minus g. Okay. So, because f and g are continuous function, piecewise differentiable functions, f minus g is also piecewise differentiable function. So, you have whose Fourier coefficients are Cn e power I n omega naught x, n is from minus infinity infinity, should converge to, by the theorem it has to converge to f minus g, which is equal to, what happens to this, which is right f of x minus g of x, and we know that Cn is 0. So, that means the whole thing is 0. So, this implies f x equal to g x for every x in minus L by 2 to L by 2. That is where f is continuous. Okay, so, we have to write for every x wherever wherever f and g both are continuous. Okay. So, that means we have seen, so the piecewise differential function means, let us say, wherever period functions in minus L by 2 to L by 2. Okay. L by 2 with Fourier coefficients for every x, for all x at which f and g are continuous. If they are piecewise differentiable functions, and this means obviously it should be continuous for all x in this, okay, in the open interval. That shows that this is a unique Fourier. So, you get a unique Fourier series once you have unique Fourier coefficients. This is one corollary, one result which immediately you can say after this convergence, after this theorem, and you can also say one more result, that if f is, if f dash of t, if f dash of x is piecewise continuous, then limit n goes to infinity c n times Fourier coefficient of f, you call this f n, is going to be 0. Okay. So, what does it mean? That is f n of f n behaves like order of 1 by n power 1 plus alpha. Alpha is positive, right? Otherwise, this is not going to be 0, this limit, right? N power alpha, then it will be n into f n will be order of 1 by n power alpha, alpha is positive. So, as n goes to infinity, that goes to 0. So, this is true. So, how do we prove this one? This is from Riemann-Lebesgue lemma. So, if f of x is piecewise continuous, that Fourier coefficient is Fourier coefficient of its derivative df by dx f dash n. Fourier coefficient is defined as 1 by L minus L by 2 to L by 2 f dash of x e power I omega I n omega naught x dx. To do the integration by parts, what you gain is e power, so what you get f x integration by parts, if you do I n omega naught x okay, from minus L by 2 to L by 2 1 by L minus integral 1 by L minus L by 2 to L by 2 f x, you do the integration here. So, you will get I n omega naught into e power itself I n omega naught x dx. So, 1 by L of this is a Fourier coefficient. So, you will get and this one will be 0. So, both will be 0, you can see. Okay. This will not be contributing. So, what you get is minus I n omega omega naught is 2 pi by L 2 pi by L square, it is a constant, Anyway, this is your Fn. So, you can easily see that this quantity Nfn by Riemann-Lebesgue lemma, we know that if it is a Fourier coefficient of a function f dash is which is piecewise continuous, implies its Fourier coefficients defined, implies it is integrable and it is square integrable, implies it is Fourier coefficient, Bessel inequality is true. So, from the Bessel inequality you have a Riemann-Lebesgue lemma that shows that this is going to be 0. What is this Fn dash? This is nothing but n times Fn into minus some constant as n goes to infinity equal to 0. So, that constant is, if you write, minus I n 2 by L square equal to minus I n 2 by L square, this constant times this, because of this is 0 and this has to be 0, n f n as n goes to infinity. So, this means this has to go to 0, this limit n f n goes to infinity, this is 0. That shows that, so alpha is actually 1, so is equal to 1, okay. Strictly speaking is like order of 1 by n square, that is exactly what you get in the corollary, okay. So, you can go on doing like this. If f dash itself is a piecewise differentiable function, that means f double dash is piecewise continuous, implies n square f n is 0 and so on, okay. You can go on doing like this recursively. So, what is that we have done so far? So, if f is a piecewise a differentiable periodic function, the Fourier series converges to the function itself. Because f is continuous in the interval minus L by 2 to L by 2 open interval, this converges to f x. If the endpoints are same, the Fourier series actually converges to the function f itself, f of x, when x is the endpoints. If endpoints are different, the average values of the function value at the endpoints is the limiting value of the Fourier series at the endpoints, okay. This is what we have seen. This so far we have used only differentiability of the function f, piecewise differentiability, piecewise differentiable function f, okay. So, these are actually sufficient conditions for the Fourier series convergence to the function f. So, we will define what is a delta function and we will prove the sufficient conditions in the next video. Thank you very much.